All right, so now that we've gone ahead and looked at these inverse trig derivatives, let's do a couple of examples about getting a derivative that involves these somehow. Example 7, find the derivative dy dx given that I have y is equal to sine inverse of 3x to the fifth power. So the first thing I'm going to note here is that there is a sine inverse in here, arc sine, whatever you want to call it. So I'm going to go ahead and just write that derivative on the side so that I have it for reference. Let's see if I can write it right here. We know that the derivative of arc sine of x is 1 over the square root of, is it 1 minus x squared or x squared minus 1? Yeah, 1 minus x squared for this one. All right, so I'm just keeping that as a note. So looking at this example 7, the first thing I'm noticing here is that I have more than one layer to this function. So let's go ahead and try doing it as that layer list. So let's list the layer and then the derivative after. So what is the outermost layer of this function? Yeah, so the outermost layer here is arc sine, or you say sine inverse, whichever. They're interchangeable. Sine inverse of whatever. And we know what the derivative of arc sine is. Usually the derivative of arc sine is what I have up there. But I have to be a little bit careful because it's not going to be 1 minus x squared. It's going to be 1 minus that same layer squared. In other words, whatever is in here, that's going to go into this layer. What's my secondary layer for this function? Yeah, I got 3x to the fifth. And then we know what the derivative of 3x to the fifth is. What's that derivative? So we can definitely use the power rule. So we can bring down to 5. And I'm going to go ahead and just multiply it because we can do that multiplication real quick. What's 5 times 3? There we get 15x to, what's the power? So if I take the power for this, the derivative, we do 5 minus 1, giving me a nice 4 because of power rule. Bring down the power, reduce the power by 1. All right, and do I have any other layers to a function? A yes or no? So we don't have any other layers because I've accounted for everything, right? I have the arc sine, I have the 3x to the fifth power. So now we have everything I need to take the derivative. Dy dx is equal to derivative of the first layer, which was 1 over the square root of 1 minus, what's going to go into this parentheses here? Yeah, exactly, 3x to the fifth. It's a little hard to see that 5 right there. But remember, we're using the same thing that was in here in the derivative layer. So that's my first layer times the derivative of the second layer. So times 15x to the fourth. And let me write that little thing right here a little bit clearer so that's easier to see. That's 3x to the fifth squared. Close it. All right, and then we have our derivative. Again, granted unsimplified, but that's not what I'm concerned about. So for the sake of going through this, I'm going to say that this is good enough for us. If you want, you could simplify. There's not much that needs to happen here. The best you can do really is put that 15x to the fourth on top. And then if you want, you could square that 3x to the fifth. But we have an equivalent solution either way. All right, so any questions about this example 7? There's a little bit of mix of a chain rule and then the derivative of my arc sine function. Great, so we're done with this one. Let's go on to example 8. Similar instructions, find the derivative. This time we're given y is equal to 7x cotangent inverse of x. What rule are we going to need to get this derivative? Or which rules? Yeah, so it looks like the biggest rule that I'm really using here is probably the product rule. We are going to use a lot of those other rules, but the biggest thing I wanted to point out here is product rule, because I have two things being multiplied. If I'm using product rule, what can I label as my first from here? Yeah, I heard someone say a 7x for my first, and then everything else can be my second. Again, one small thing I want to note, remember cotangent inverse. Don't make the mistake of saying this is the second, because it has to be cotangent inverse of something. All right, so now we're just going to go ahead and follow through with the product rule. The product rule states that the derivative of a product, we said it at the beginning, is the first, so 7x, times the derivative of a second. What's the derivative of arc cotangent? Again, yes. This is my d second. And this was my first over here. So first d second plus the second. We just copy down the second, cotangent inverse of x, times the d first. What's the derivative of my first? Yeah, we just have a plain 7. And then we're done. We've done the calculus portion at least. Again, granted, unsimplified, but that's not our concern for now. The main point of this example was recognizing that it is a product rule, where 7x was one part, and then cotangent inverse or arc cotangent of x was the second part. All right, great. So we're done with example 8. I'll give y'all some time to copy as needed. All right, so moving on to our next example. Example 9. So what I'll actually have y'all do is take a moment to see if you can complete this problem. This one does require a good amount of rules. But in particular, I would recommend that you list out the layers of your function here. We have cosecant inverse of e to the 8 sine of theta. As your starting hit, there should be a total of basically 3 layers here. So identify layer number 1, number 2, and number 3. I'll give you all roughly maybe like 5 minutes to see what you can do with this. So I'm going ahead and starting y'all off, if you haven't done so, with the layers of this function. I'm going to go ahead and start filling out this table. Again, you can check if you have the right idea as I go through it. And I'm just using these stars as placeholders to show that they're the same thing on the left and the right. All right, so I'm going to go ahead and talk about this problem. So if I look at this function, arc cosecant of e to the 8th sine of theta, I see that this has actually 3 layers. The first layer being cosecant inverse of something. My secondary layer being e to a power. And my third and final layer being 8 sine of theta. So after listing these layers, I can go ahead and take the derivative of each layer. I know that the derivative of cosecant inverse of whatever is equal to -1 divided by the absolute value of that item times the square root of that item squared minus 1. Notice here that I just put a single star each time, say whatever was in here, that's also going into this inner layer. Same thing for here, e to whatever power. We know the derivative of e to a power is still e to that power. And I'm filling in the exact same stuff on each row. And then derivative of sine, we know that to be cosine. All right, so we've done a lot of the hard work. Now all I gotta do is fill this in as one unified derivative. So p prime of theta, I have the first layer, -1 over the absolute value of whatever was in here. So in this case, it was e to the 8th sine of theta times the square root of, I don't know if I'm going to have enough room here, e to the 8th sine of theta squared minus 1. That's my first layer derivative. Times The next layer, e to the 8 sine of theta. And then the final layer, times 8 cosine of theta. I ran out of space here, but this should be times 8 cosine of theta. And then that is our final answer. And so we have example 9, a chain rule with technically 3 layers that uses my inverse trig, my exponential function, and my trig functions. So a combination of 3 different rules, essentially. Any questions, comments, or concerns about this example 9? Now let's go ahead and look at our final one. I'm going to give everyone just another minute to copy this down before I move on. We're going to do our example 10, and then we'll be done for today. So as we learn more new derivative rules, like what we've been seeing, there's nothing stopping us from combining them. Here we did a combination of chain rule, exponential, and inverse trig. The other one I did product rule with inverse trig, and so on and so on. So pretty much any combination is something that we could deal with. Now the question about how complicated it might be very tedious, but it's quote unquote doable. All right, so let's go ahead and look at our last example. Let's just do example 10. Let's find f prime of t if I know that f of t is equal to cosine inverse of t, all of that to the 9th power. And I'm going to go ahead and be a little preemptive and write out my layers. So looking at this function, again, it's important that we can identify the outer layers all the way to the inner. What is my outermost first layer? What was that? Yeah. Yeah. So the first layer being quite literally the outer layer, something to the 9th power. And then that really leaves us with just one inner layer, the whole cosine inverse of t. And then I know I'm listing the layers because I've accounted for everything already. All right, so now I just take the derivative of each layer. Derivative of something to the 9th power, we just have our power rule, which says we bring down the 9 and reduce that power by 1. And again, if you want, just for the sake of continuity, whatever's in this layer should also be in that layer. Next is the derivative of cosine inverse. Well, we know now that the derivative of cosine inverse is going to, in fact, be -1 all over the square root of 1 minus, in this case, t, not x. Just accept 1 minus t squared. We didn't have to do another layer of chain rule because we just have a plain t in there. And now we can finally get the derivative just by multiplying the derivative layers. We have f prime of t is equal to the first layer, 9 times, I don't know why it's glitching like that, 9 times whatever was inside, whatever the star was, so cosine inverse of t to the 8th power. So that's layer number 1. Layer number 2 is this big old expression over here. -1 over the square root of 1 minus t squared. One quick thing I'm going to note is that please make sure that you actually put the parentheses around the second part. Because if you just write -1 over this, especially if we're doing homework, it's going to read it as minus that expression sometimes. So we just want to put parentheses to be clear that we are, in fact, multiplying. So we have example 10. All right, so with that, that finishes up what we're going to be doing for today. I'm going to cut it class a little early today, a fair bit early, actually. But besides that, I will see y'all tomorrow, where I believe we have, one more section? I have to see what's on the schedule. But regardless, I'll see y'all tomorrow.